Hello, chemists. Jolly here. We're going to be talking about NMR today, and we're going to try it on this touch screen and see how that goes. All right, I am looking at the NMR chapter and the NMR handout. So if you have those handy, that'll help. All right, I'm going to share a screen with you. So this is the chapter. All right, so just a little background on NMR first. So we've already talked about mass spec and we've already talked about IR. Well, generically remember, spectroscopy is just the study of the interconversion of energy with matter. And so IR was dealing with the vibrations of matter, and then we could see those vibrations for different functional groups. Okay. I put a little blurb here just as a reminder, energy, either from physics class or for Gen Chem class, energy is the electromagnetic radiation spectrum, and we're only going to use part of it. And then don't forget the electrons can behave as both particles and waves. Other words, this wouldn't be possible. And then I do a little blurb here about, wavelength frequency, converting back between them, and then how to do the energy. We are not actually going to do energy calculations. That was just a reminder that we're using, those kind of ideas. All right. NMR spectroscopy, okay? Nuclear magnetic resonance spectroscopy. We're going to be dealing with two types. One is the proton NMR and one is the carbon-13 NMR. Now, in order to take an NMR, we have to assume that the nuclei of elements and isotopes behave as if they were little magnets spinning on an axis. And the proton and the carbon-13 are the ones that we're interested in, but you can do this with others. So the nuclei absorb energy when they're radiated with actually radio waves. Okay, we're talking huge, long radio waves. And then it's in an outside field. So pardon the picture here, but you're going to take, so imagine that's a hydrogen, okay? So that's a hydrogen nuclei. And this hydrogen nuclei, if you will, is creating a magnetic field. Well, that is placed inside a bigger magnetic field, and we're talking huge, okay? So there's an external magnetic field. All right, so we have these two magnets. They can either oppose each other, they can align with each other, but they're actually going to make something we call resonance. This is not resonance when you do Lewis structures, okay? This is resonating, flipping, something like that, where this can go back and forth between up and down, if you will, for the magnetic fields. It flips the magnetic fields. And then we shoot radio waves at it. I know this sounds like, ooh, that's not going to tell me anything, but having this external and the internal fields, the magnetic fields, and then the radio waves make something called NMR. And if you've been walking by the hospital, it's very similar. There's that whole area that there's a giant magnet. Same thing in essence. All right, so here we have our wonderful little NMR, and there's a couple types. So there's really old one. It's called a sweep, and it basically just uses continuous waves. So it's a constant radiation while you change the magnetic field. But this is the one I used when I was in school. It takes about 2 to 5 minutes to take a spectra. Well, luckily, that's not so for you guys. You use something called Fourier transform, and there's a superconducting magnet, and it does pulses, and it takes only like 5 seconds to come up with a spectra. Now, why did we need to know that? That was completely background information. So let's look at a generic NMR, and then I will do another short clip, and I will tell you about each piece. All right, so what to look for on an NMR? The first thing is we have to recognize that it is an NMR. And so on the x-axis is going to be parts per million, okay? And this y-axis basically tells you the height or the integration. And so we always start at 0. And then generally, we can go up to 12, 13. I'm going to put 14 right here. That's usually the maximum. And so you'll always be able to tell because it will go from 0 to 14. A carbon 13 one, okay, so this is proton NMR. A carbon 13 NMR will go from 0 to 200 ppm. So that's how you'll tell the difference between the two. And then they look a little bit different as well. All right, what else do we need to look at? Well, there's usually a reference, okay? And the reference is usually one line right here. Now, keep in mind, we can actually have the computer not print out the reference for you, but we try and put the reference right there. And luckily for the proton NMR, it shows up at 0, so you wouldn't include it in your interpretation anyway. All right, I'm going to flip over to the handout. If I can find it, there we are. All right, so this is the handout for NMR spectroscopy. And everything that I'm going to talk about is listed right here, but we're going to go over each of the pieces. But the ones that I just talked about is the x-axis, whoops, that's not right. But the x-axis goes from 0 to 14. The reference is called trimethylsilane, and that is at 0 ppm. And I just wanted you to see a picture of it. And this wonderful thing down here that has been labeled for you is an average picture. All right, this is a very, very short clip. All it talks about is the basics behind it. Are you going to be tested, of course, on it? No, but it's nice to know why you can get an NMR spectra. Okay, we have to have nuclei that basically behave as magnets. We put an external magnet on it, and then we shoot radio waves at it, and then we can detect, okay, from that. We're going to be using proton NMR and we're going to be using carbon 13 NMR. And how do you tell the difference? Because the scaling on each of them is different. And then the reference point is actually going to show up a little bit different in the carbon 13. All right. The next one, we will talk about the individual details.